Year 200 BC. Location Syracuse, Sicily. A well-known engineer by the name of Archimedes is approached by King Hiero II. The king asks Archimedes to design him a ship worthy of a king. The luxury ship would be named the Syracusia after their hometown. This ship would come to be known as one of the largest of its time, being able to hold at least 1,600 tons of cargo and approximately 2,000 people. Archimedes was faced with a problem. Big ships have big hulls, and at the time, big hulls meant big leakage. In order to deal with the enormous amount of water that would leak into the ship, Archimedes designed a device that consisted of a screw that could be turned inside of a pipe in order to create a simplistic pump. With each turn of the screw, water would lift up the pipe. This is one of the earliest mechanical engineering devices, and it became known as the Archimedes screw. Year, approximately 132 AD. Location, China. Current rulers, Han Dynasty. In ancient China, an earthquake symbolized that the current rulers had done something wrong in order to upset the heavens. One of the possible wrongdoings was ignoring the needs of the common person. In order to restore balance and help the people affected by the earthquakes, an engineer by the name of Zhang Heng presented an ancient seismometer to the Han government. On the outside of the seismometer were 8 dragons with small balls in their mouths. They were equally spaced out and pointing to 8 different directions. When an earthquake occurred, a pendulum inside would swing, releasing a ball which activated a lever for one of the dragons. This caused the ball in the dragon's mouth to fall into the mouth of a toad, which would indicate the direction of the earthquake. Zhang Heng's device represents an early mechanical device used to accurately detect the direction of an earthquake and acts as a precursor for modern seismometers. Let's jump forward to around 200 AD, but still in China. Imagine that you are a soldier and you're out lurking at night. It would be easy to get lost, right? How would you find your way back home? In order to solve this dilemma, the engineer Ma Jun created a compass-like device known as the south-pointing chariot. The chariot used a system of differential gears in order to ensure that a doll positioned on top of the chariot was always pointing south. Although the chariot was not always accurate or precise, it could be used for simple navigation. Year, approximately 1206 AD. Location, northern Mesopotamia. An engineer by the name of Al-fadzri was working on his book titled The Book of Knowledge of Ingenious Mechanical Devices. He is credited with creating the camshaft and the crankshaft, both of which are considered basic building blocks for any mechanical device in the modern world. He used these devices in order to create one of the first known double-action pumps with a suction line. According to Wikipedia, Al-fadzri's double-action suction pump could lift 13.6 meters of water with the help of delivery pipes, which was quite impressive at the time. Al-fadzri used his knowledge of mechanical systems in order to create one of the first water delivery systems that used gears and hydropower. Using the system, he was able to supply water to mosques and hospitals that needed it. Time, 17th century. Location, England. The 17th century marked a huge moment for engineering. Sir Isaac Newton had created calculus and formulated his 3 laws, which are: an object's velocity remains constant unless acted upon by net force. The net force on an object is the product of its mass and acceleration. This is commonly seen as the formula F equals ma. When one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. Newton's discoveries sparked a more numerical and analytical approach to engineering. Mechanical engineering really became its own discipline in the 19th century. Mechanical engineers were needed in order to create, power, and run the new machinery that came during the Industrial Revolution. As you can see, mechanical engineering has consistently involved the creation and analysis of mechanical devices in order to benefit humanity. However, the mechanical engineers of today have a much broader toolset than the engineers of the past. Typical mechanical engineering curriculums consist of math, namely calculus, linear algebra, and differential equations; statics and dynamics. Statics is the analysis of systems in equilibrium, so the acceleration and net force is equal to 0. Dynamics is the analysis of systems in motion, therefore the net force is not equal to 0. Both consist of analyzing solid systems. Then there's solid mechanics. Solid mechanics is the analysis of how an object's motion and deformation is affected by various factors like force and temperature. Thermodynamics. Thermodynamics is a study of heat and temperature as they are related to work and energy. And then there's heat transfer. Heat transfer is pretty much what it sounds like. It's the study of how thermal energy is transferred between things. And then fluid mechanics. Fluid mechanics is like statics and dynamics, but for liquids, gases, and plasmas. As you can see, math, statics and dynamics, and solid mechanics all echo the mechanical engineers of the past. They are the building blocks for many mechanical devices. However, today's mechanical engineers are also using thermodynamics, heat transfer, and fluid mechanics as a part of their toolkit. The future of mechanical engineering looks very exciting, and I believe there will be lots of hybridization with other disciplines. The first exciting field is in micro-electromechanical systems, or MEMS. MEMS are tiny mechanical devices that are combined with electronics. They are typically about the width of a human hair. An example of MEMS technology is the accelerometer in your phone. An accelerometer is a thing that your phone uses when you play games to track tilting and rotational movement. The next exciting field is biomechanics and biomedical engineering. This field of mechanical engineering involves combining biology and engineering in order to do things like build artificial body parts or mechanical medical devices. Some cool examples of mechanical medical devices would be hearing aids and artificial hearts. The third field is alternative energy. Solar and wind energy are rising in popularity, and mechanical engineers will play a large role in making these technologies more cost-effective, safe, and efficient. Then we have mechatronics, which is the combination of mechanical, electrical, and software engineering. The three are combined in order to essentially automate things. Examples of mechatronics are robots or even the autofocus on your camera. Lastly, there is computational fluid dynamics, or CFD. This is an area of study where computers are used to analyze what happens when a fluid is in motion. For example, CFD is used to see how well a spaceship will perform or how well a plane will fly. These are just a few of the exciting fields emerging in mechanical engineering. So you've seen the history, the coursework, and a bit of the future for mechanical engineering. What do you think? Is mechanical engineering right for you? Also, don't forget to leave a comment about which discipline you want me to cover next. Thanks for watching, guys, and I'll see you next time.